Welcome to MRU E-Learning powered by Mallareddy University. Myself, I am Dr. T. Viska, Assistant Professor in Data Science Department, School of Engineering and Mallareddy University, Hyderabad. And today the topic I am going to discuss is about compiler design. So we know what is a compiler. What is a compiler? Compiler is a translator which converts or which translates high-level language to machine understandable language. So that is, the input to the compiler is the source program, and the compiler performs some operations, and the output of the compiler is the machine code, language understandable by the machine. So let us see what happens in the compiler. Compiler has two parts, analysis part and synthesis part. So the analysis part will analyze the code, source code, and it will convert that source code into intermediate code, and it gives that intermediate code to synthesis where the actions are performed and the target and the machine understandable code is available in the target program. So this is the analysis part and synthesis part. Source code is given to as input to the analysis part. Source code is nothing but our high level language code, and in analysis part it is the front end. So in analysis part it is converted to intermediate code representation, that is the input to the analysis part is the high level language code and the output of the analysis part is the intermediate code representation, and this output intermediate code representation is given as input to synthesis part, and the output of the synthesis part is the low level language code which is understandable by the machine. So the compiler has total 6 phases. So we said that compiler consists of two parts, analysis part and synthesis part. So here the 6 phases of the compiler is divided in such a way that 3 phases are in analysis part and the other 3 phases are in synthesis part. So the 6 phases of the compiler are lexical analysis, syntax analysis, it is also known as parsing, semantic analysis, and intermediate code generation, code optimization and code generation. These are the phases of the compiler. So these are the 6 phases of the compiler. So front end consists of 3 phases, lexical, syntax and semantic, and synthesis part back end consists of 3 phases, intermediate code generation, code optimization and code generation. Let us see about lexical analysis, first phase of the compiler. So the duty of the lexical analysis is it scans the source code character by character and group these characters into tokens based on the syntax rules. The token is the smallest unit of meaningful data in a programming language. So tokens, we can call it as tokens can be keywords, identifiers, numbers, constants, operators, punctuation marks. These everything are called as tokens. For example, I have a statement A is equal to B plus C. So in this, let us see how many tokens are there. So A, B, C are identifiers. So these are variable tokens. So these are 1, 2, 3, A, B, C are tokens, and symbolic tokens, that is equal to plus, are also tokens. So in the given statement, we have 5 tokens. So lexical analyzer scans this statement from left to right, identifies these tokens, and these tokens are saved in the symbol table. For example, let us see an example. So we have given a statement, position is equal to initial plus rate into 60. So we are giving this input to the lexical analyzer. Now lexical analyzer scans the input from left to right, and now it identifies the tokens and keeps that token in the symbol table. So first it sees position. Now it translates that position into ID1 in the symbol table. And initial is an identifier. It translates that initial into identifier 2 and places that in the symbol table. And rate is another identifier. It identifies that identifier as ID3 and places it in the symbol table. So from next time onwards, for the next operations, instead of position, initial and rate, we use ID1, ID2 and ID3. And equal to is a token, plus is a token, star is a token, and 60 number is also a token. So lexical analysis, in lexical analysis, lexical analyzer identifies the statement as tokens and keeps that token in the symbol table. So this is the symbol table. We can see 1, 2, 3 here. So position, initial, rate, these are kept in the symbol table. Position is taken as ID1, initial ID2, and rate is taken as ID3. So let us see this. So here we have lexical analyzer, syntax analyzer, semantic analyzer. Let us see what happens in these phases. So these are the analysis part. So first the input to the lexical analyzer is position is equal to initial plus rate into 60. So position, the output of the lexical analyzer is position is taken as ID1 equal to same equal to, initial is taken as ID2 and rate is taken as ID3 and remaining number is taken as 6p, remaining same, the token plus and asterisk. Now this is the output of the lexical analyzer. So lexical analyzer stands the input and it identifies the tokens and places the tokens in the symbol table, and the output of the lexical analyzer is the representation what it has given in the symbol table for the particular tokens. Next, the output of the lexical analyzer now is given as input to the syntax analyzer. Now the duty of the syntax analyzer is it will form a parse tree here. So it will check whether the grammar is correct or not here. So first it will convert the input string into parse tree here. So it breaks at the operators. So here first it is breaking it equal to, next it is breaking it plus, and next it is breaking it star, that is equal to, it will take left side expression is ID1, right side expression it will take completely like ID2 plus ID3 into 60. It takes in that way. Okay. Next again it breaks down at plus. Now again it is converting to ID3 and ID2. Here it is ID3 into 60. Again it breaks at operator into and it is ID3 and 60. So that is what we have in as the output of the syntax analyzer. How it is dividing the expression, like the left side expression, right hand side expression, and which operator it is breaking, we will see in the context free grammar when we study about syntax analyzer in coming slides. So this is the output of the syntax analyzer. Next, the output of the syntax analyzer is given as input to the semantic analyzer. Now the semantic analyzer, it checks the meaning. It checks whether everything is in the correct way or not. That is, whether the type of the variables where you are, type of the values which you are multiplying, are they same or not. In that way it will check it. It checks the meaning, semantic analyzer. Now here 60 is integer and here position, initial and rate identifiers are of type float we have taken. So here ID3, we are multiplying ID3 into 60 in the output of the syntax analyzer. But ID3 is of type float and 60 is of type int. So here we are multiplying to different types. So this is not correct. So the meaning is not correct. So what semantic analyzer will do? It will convert the integer part into float. That is, it will type as 60 to a floating value. So this is the output of the semantic analyzer. So this is the analysis part. I said analysis part has three parts: lexical, syntax and semantic. So it is analyzing the statement DP and it is checking whether at every step it is correct or not. If it is not, semantic analyzer is adding meaning to that. So next let us go to the synthesis part. Is that the synthesis part is intermediate code generator, code optimizer and code generator. So here the output of the semantic analyzer we have seen, it is converting into float. Now this output of the semantic analyzer is given as input to the intermediate code generator. Now here intermediate code generator will give intermediate statement like intermediate code statements here. So it will convert the complete input statement what we have given using temp values. So first the steps we have T1, that is temporary variable 1, T1 is equal to, first step what we are doing, we are converting integer to float. This is the first step. Then after converting integer to float, what we are doing? So again we are taking another temporary variable T2 and we are multiplying the output of T1, we are multiplying T1 with ID3. So this is the second step what we need to do. And next T3, next variable, and we are adding the T2 value to identifier 2, and lastly whatever the value is there in temporary variable, we are placing that value into ID1, that is position here. So here it it has the steps in which order we need to execute the particular statements. So this is the output of the intermediate code generator, that is some action is performed here. Next the output of the intermediate code generator is given as input to the code optimizer. So here code optimizer will check, can we reduce the code? We have 4 lines of code. Is there any possibility to reduce the statements, number of statements? So here what the output of the code optimizer is, so it is combining the statements here. So T1 and T2 is combined and directly it is written as T1 is equal to ID3 into 60.0, that is floating value. So instead of taking one statement, converting it to converting into float, so directly what we are doing here, directly we are writing 60.0, which is a float value. Directly it is multiplying with ID3. And again, instead of storing the result in temporary variable T3 and assigning that value T3 to ID1, it is directly storing the value into ID1 by adding ID3 plus T1. So this is the code optimizer output. So what code optimizer is doing is, it is optimizing the code, reducing the statements wherever it is possible. Next, the output of the code optimizer is given as input to the code generator. The output of the code generator will be a machine code. So here whatever the statement, whatever the statements we got as output for the code optimizer, the statements are converted to machine language code here. So here first statement is load. Load F represents floating numbers. Since ID1, ID2, ID3 are of type float, the F represents float value. So load, first LD is load, that is we are loading ID3 value into R2 register. Next we are multiplying that R2 value with 60 and placing the value in R2. Multiply what we are doing, it is R2 is equal to R2 into 60. R2 is nothing but ID3. So this is ID3 into 60, that value is placed in R2. 60 is 60.0. Yeah. Next load. Again the value is ID2 value is loading into R1. So now R1 has ID2 value. So just we are loading here into R1. Next adding R1 and R2 and we are storing the result in R1. So R1 consists of ID2 plus ID3 into 60.0. Now the result is present in R1. Next we are storing the result. ST is storing the result R1 into ID1. That is R1 is stored in ID1. So in this way the code generator gives the machine code as the output for the given input statement. So this is the process in which high level language is converted into low level language understandable by the particular machine. So this is the complete phases of the compiler which we have studied here earlier. So now coming to second phase of the compiler. So the second phase of the compiler is syntax analyzer. It is also known as parsing. So here the syntax analyzer checks the grammatical phrase of source program. So it checks whether it is the statement what we have given is according to grammar or not. So if it is not according to grammar, it gives us an error message which we need to rectify it. So what parser will do? So parser obtains string of tokens. It gets the tokens from the lexical analyzer. It groups the tokens in the input in order to identify larger structures in the program. Next, if any syntax error is there, it should repair that error in the program. And also, it should also recover from the errors so that it can continue the rest of the input. So where the parser is, the position of parser in compiler design. So the source program is input to lexical analyzer. Lexical analyzer will group the tokens, places the token in the symbol table. Next, the parser will get the tokens from the lexical analyzer, and based on the tokens, it will form the parse tree, and that parse tree is given to the rest of the front end, that is to the semantic analyzer, and semantic analyzer output is intermediate representation. In that way, it continues to the other phases of the compiler. So the specification of syntax of programming language. The language syntax specification should be unambiguous. There should not be any confusion for the system when we give a grammar. So let us see this one. So parsing algorithm, we have two approaches, top-down approach and bottom-up approach. And also we have special tools which can automatically generate a parser for a given grammar. So the tool we use is Yath tool, yet another compiler. This is a compiler generation tool available in Unix which generates bottom-up parser. Now let us see context-free grammar, that is the grammar which we use in syntax analyzer to check whether the given statement is according to grammar or not. We use here context-free grammar. The context-free grammar consists of terminals, non-terminals, start symbol and productions. So this is the representation of the grammar. G is equal to T terminals, N for non-terminals, and S is start symbol, P is production rules. So here these are the productions. What are the productions given? So E tends to E cross E is a production. E tends to E plus E is a production. E tends to ID is a production. This complete thing is grammar. Okay. And the start symbol is same here, E only for here. This will give the start symbol. And what are the terminals here? ID is the terminal. Okay. Like the small case variables and operators will be taken as terminals here. Capital letters will be taken as non-terminals here. Now, based on this grammar, they have given a string ID plus ID cross ID. Now, this is the input string. Now, we should check whether this input string is correct or not. It should check whether it is according to syntax rules or not. How it will check? Based on this grammar, if we are able to produce this input string, then it will say that yes, it is the correct representation of the input string. Otherwise, it gives us an error. So here first we are starting from E tends to E cross E. So here E cross E, this E is replaced by E plus E. Next E can be replaced by, this E can be replaced by ID. Next the non-terminal, this E can be replaced by ID. And next non-terminal, this E can be replaced by ID. And at the end of this thing, we are at the end of this process, we are getting E tends to ID plus ID cross ID, which we are able to get this from the given grammar. So we can say that yes, this string is according to the syntax rule. But here, like while generating this input string, your system generates this input string, but while generating this input string, it has a confusion because here it has taken E tends to E cross E grammar and it is able to produce this string. And here this is again like it can also start with E plus E, and also it is able to produce this string. That is, this E is replaced by E cross E, and this E is replaced by ID, this E is replaced by ID, and this E is replaced by ID. That is, either by taking E tends to E cross E, or either by taking E tends to E plus E, in both ways it is able to get the input string. So here the system has a confusion whether it should follow this path or this path. So in order to avoid that, that is, the grammar is ambiguous. So whatever the string we have, whatever the statement we have taken here, E tends to E cross E first it has taken, then here it has taken E tends to E plus E. So here it is E tends to E cross E, here it is E tends to E plus E. So here in both ways it is able to get this string. So here it is ambiguous. Your system will confuse in which way it should go, whether in that way or whether in this way. So here actually how the statement executes, if I have ID1 plus ID2 cross ID3, actually the highest preference will be for multiplication. So this should be executed first, and whatever the result you get, that result should be added to ID1. Actually this is the process. So here first in this process, here it is correct, it is wrong, because so here when we come to leaves, the process of execution starts from bottom to top. That is, first E cross E will be executed, then it is added to E plus E here in this one. Here E plus E is executed, after that it is added to, after that is multiplied with E, which is wrong. So this is correct, but here system confuses which one to follow. So there is an ambiguity here. Ambiguity is confusion. So in order to avoid that confusion, we need to change the grammar to unambiguous grammar. So to convert the grammar to unambiguous, we should take care of associativity, and also we should take care of precedency. So you can see this one. So here precedency, highest precedence is given to multiplication, then to plus. So this order we should follow, that instruction should be given. And next left associativity, that is, if I have more than one addition here, more than one addition or more than one any operator, same operator, then what should I do? I should first go with this and then the result should go with this. That is, left associativity should be maintained here. But for some, suppose I have something like some 2 power 3 power 4. So here, suppose if I have in this way. So first what should be executed? First 3 power 4 should be executed, then 2 power that should be executed. So this is right associativity. For powers I will go with right associativity. So we have some rules for particular operators, whether we should follow left associativity or right associativity. Now we are changing the grammar, ambiguous grammar, that is the grammar which has confusion, to unambiguous grammar. So what we are doing here, E tends to E plus E, E tends to E cross E, and E tends to ID. This is the grammar given. So already we have seen with this grammar we are getting ambiguity. So for that reason now we are converting the grammar. In what way we are converting? We are changing E tends to E plus E to E tends to E plus T or T. We are adding extra T here. And we are changing this E cross E to T tends to T cross F or F. And we are changing this E tends to ID to F tends to ID. So here the meaning should not change. If you are changing the grammar, the meaning should not change. How you are changing this grammar? Here I have E tends to E plus E. So this second E I am replacing it with T. And also I am taking another production T also, because I should not miss E cross E for E. So here if I have ID cross, ID1 cross, ID2 something like this. So start symbol is E only. But I should directly go to this one. So how I will go? E tends to T I will go in the given grammar, and T tends to T cross F I will go, and T should be replaced by ID and also F should be replaced by ID. So what I am doing here? T tends to T cross F, or F also I am taking, and also F tends to ID I am taking. So T is reduced to F and this F is reduced to ID and this F is also reduced to ID in that way. Okay. So the meaning of the grammar should not change. You should take care of that. So in this way we have converted ambiguous grammar to unambiguous grammar. And now let us check whether there is any confusion for the system or not. So here I have taken ID plus ID cross ID. Let us check this one. So ID plus ID cross ID. So which one I can take? So my start symbol is E here at the given grammar. Now what is my given grammar? This is the given grammar. This is unambiguous grammar which I have converted from ambiguous grammar. I changed it. Now here E is the start symbol. I have only two options. Either I can go with E plus T or I can go with E tends to T. So I should start with these two only. Since I have a plus here, so compulsorily I need to go with this E tends to E plus T only. I don't have any other way here. So next, now again E plus T I have taken. Next this T can be replaced by either T cross F or F. But I have asterisk, there is multiplication sign in this one. So what I will do? I will go with the T cross F. I don't have other option. So just I have gone with T cross F. Next this E should be replaced by ID. This E should be replaced by ID, T should be replaced by ID and F should be replaced by ID. So for that I have again two options for E. Either I can go with E plus T or I can go with E tends to T. But here just reducing E to ID only. So I don't have any other place there. So I will take this one here. I will take this one. That is E is changed to T. Remaining things as it is I have taken. And next step this T is changed to F. And remaining things as it is I have taken. Next now this F is changed to ID. Remaining as it is I have taken. Next this T is changed to F. Next F as it is I have taken this one. Next this F is changed to ID. This F is also changed to ID. So I am able to produce this string from the given unambiguous grammar. Only one way I have. I don't have other way to get this input string. So in this way we have converted ambiguous grammar to unambiguous grammar. Now system will not have any confusion. So this is the whatever the input string we have traced with it. So this is the parse tree for that. So how we have achieved that? E is changed to E plus T and T is changed to T cross F and here T is changed to S and here E is changed to T, T is changed to F, F is changed to ID and here also this F is changed to ID and this F is changed to ID. You collect all the leaves. So what are the leaves here? ID plus ID cross ID. So you collect these leaves, we will achieve this one. Then we can say that, then your system says that yes it is according to the grammar. There is no errors, it will not display any errors. Otherwise, if you are not able to achieve this input string from the given grammar, it shows us the error. The particular error is present in this particular line. This is compiler error recursion. Now, elimination of left recursion. So here, A tends to A alpha. So if I want to substitute this one, it continuously goes in this way. A tends to A alpha, A tends to A alpha. It is going in the left recursion format. So we need to avoid that. So in order to avoid that, this is the formula. So what productions you have without this A, take those productions and add A complement. Without A, I have this production. A tends to we speak a complement I will take. Next, this a complement, what productions have a, you select that one. That is this as a. So now avoid that a and take the remaining string. So what is the remaining string I have there? Terminals I have there, alpha. To that one, just add a complement and an epsilon here. So when you substitute this, you should get the same thing. Meaning should not change. In that way, we will eliminate the left recursion. So how, for this is an example, how we are eliminating the left recursion. So here we have the productions without a, start symbol is a. The productions without a, what are the productions without a? BD and epsilon. So take the productions and add a complement after that string. So this is a tends to BD, add a complement, and epsilon nothing, so add a complement. Next, for a complement, take the productions which have a, this thing. Other than a, take the other remaining string. That is, here it is C and here it is AD. Just add a complement beside that and add an epsilon. So this is the method to eliminate left recursion. So change the grammar by eliminating left recursion into this format. And left factor the grammars. So here left factor the grammar listens. Here we can see if I want to replace suppose I have a string starting with some alpha. So this is the start symbol. I should start with start symbol and I should place the string actually. So here this is the start symbol. So in my input string I have something starting with alpha. Now your system has a confusion. Which production it should take? Either it should take alpha beta or it should take alpha gamma. It has a confusion. In order to avoid that confusion, we are left factoring the grammar. So the grammar, how we left factor the grammar? Here we have a tends to alpha beta, a tends to alpha gamma, so on. So here which string is repeating? Take that string. Here what is repeating? Alpha. So take that alpha. And beside that take a complement. And next for a complement productions, so which strings are not repeating? That is the strings beside repeating string. That is beside alpha is repeating. Beside alpha I have beta and I have gamma. So take that productions in a complement. If you again substitute a complement, you should get the same grammar. Meaning should not change. That care we should take. For example, I have a tends to AB and B is the in first production, B is non-terminal and ABC, and B tends to some BDE. So that is 3 productions I have, 4 productions I have, that is A tends to AB, A tends to ABC. So this combinedly I have written in this here, and B tends to BD, B tends to E, combinedly I have taken. So the input string given is ABC. Now my start symbol is A. I should start from A and I should check whether that string is achieved or not. So first what I am doing, suppose I am going with the first production, this AB. So here I am replacing AB with A and B. So for B I have B and D, which is ABD I am getting. I am not achieving ABC. Now I will backtrack. Otherwise I will replace B with the E. I will replace B with the E. But here also I am not achieving that. So again I should backtrack up to A. Again I should start with another production now. I have gone with AB. Now I should go with ABC. Now here yes, we are achieving the particular string ABC. So here the time is wasted. Again it should backtrack and check for each and every step. This simple string is okay. If a string consists of more number of terminals or more number of terminals and the statement, then it will take more value. So what we should, more time it will take. So for that reason, what we need to do? We need to left factor the grammar. So how we are left factoring the grammar? Take this statement, production, and which production is starting with same value. So here this is starting with A and this is also starting with A. So take that common. A tends to A. Beside that, keep the A complement. Now take A complement tends to. Now which is left here after taking A? B. And which is left here after taking A? B, C. So take that production into A complement. Now this statement don't have any repetition of the particular terminal. So no need, just keep it as it is. No need to left factor the grammar, this for B production. In this way, we are left factoring the grammar. Why we are left factoring the grammar? We are left factoring the grammar in order to avoid confusion for the system to take which production here. If the both productions are starting with same termini. So this is an example. S tends to IETS, that is if expression then statement. And another production is IETS, ES, that is if expression then statement, else is statement, or A is a statement. And E tends to be this, and this is the string I need to start from S and I need to achieve this one. So here again, is there any possibility do we need to left factor the grammar? We need to check here. Yes, both are starting with IETS and IETS. So there is a need of left factoring the grammar. So left factor the grammar. How to left factor the grammar? S tends to, which is repeating. IETS is repeating. So beside that, repeating part take, and just beside that, take S complement. Okay, start symbol complement. S complement. Next, for this and I am taking A as it is, no repetition, just extra production, just I am keeping that. Next, for S complement, what I should write? I should write the terminals or statements which are after this repetition part. So what is there after this? Nothing. So I will add an epsilon. What is there after this? ES. So it is like epsilon ES, which we have written as ES of epsilon. Everything is set. So in this way, we have left factor the grammar, given grammar, in order to avoid confusion. So these are the types of parsers. So parser is of two types, top down parser and bottom up parser. And top down parser, again we can achieve that using recursive descent parser and LL1 parser. And bottom up parser is of two types, LR parser, operator precedence parser. LR parser, again it has LR, SLR, LLR, CLR. So whatever the grammar, to achieve always, first we need to check all the, whether it is ambiguous grammar. If it is ambiguous, change it to unambiguous grammar, and eliminate left recursion and left factor the grammar. We should keep all this ready before going to implement these parsers here. I am ending this. Thank you.